Right, we move from linear combinations to spanning sets. And so our spanning set is just the set of every linear combination of a set of vectors. That does make our first step here of writing a vector equation a little more challenging because we don't have a result, right? So writing the equation, we have to come up with what the heck is on the other side of that equation. Now we do know spanning is all about our linear combinations. So I'm going to do the lazy version here. I'm going to label my vectors, and I'm going to go ahead and write that linear combination of all of my vectors. All right, so right now I am not done because I need an equation, and we don't quite have one. So the goal here, if we want to talk about the set of all vectors that, we care about the set of vectors spanning, right? Not just what the spanning set is. We want that spanning set to equal R4. So we need to basically say we need to hit some vector, every vector, in fact, in R4. So let's just make up a vector here, a W. That's good. So now we're saying if I make a linear combination of these four vectors, it should equal some vector W. And now here's the thing, like I said, it has to be for all vectors and all for R4 if we're going to span. And we need to talk about our solutions. So we could write has at least one solution for all vectors in R4. Perfect. Now, we want to get a little more into the weeds on this because we have exactly four vectors and we're talking about spanning R4, which is a four-dimensional space. We could say these have exactly one solution because there's no way that we could have a linear dependent vector in this space, but in this set. But that's getting beyond what it's asking. If you want to just make sure you're always hitting this, we need our consistency. We need at least one solution. So we get that statement about the solutions. And we do need that for all because we want to span R4, which means this vector W has to be every single vector possible in R4. We had some just questions about whether or not we could have the zero vector here. The zero vector, it becomes a little sus as you're equal to here, because if you had dependent vectors, it's possible to not span and still equal the zero vector. Now, if we were getting a consistent system with this particular set of vectors with that zero vector, again, dependence is possible without spanning, but if we said it had exactly one solution, well then I think we'd be okay only because we have four vectors. But again, that's when it gets really gray. So this is the cleanest way to write this problem without trying to overcomplicate it. And it really fits with what we're trying to do. We're trying to say we can write every vector in R4 as a linear combination of those four vectors provided, and that's exactly what this sentence says. All right, so then we look at the next question, number 2. It says, use our matrix below to determine if our statement was correct. So they've taken our four vectors and they've shown us definitely no. We only have 2 pivot columns, and then we have these 2 non-pivot columns, and you can decide how you want to write this. I was accepting anything like, first we need to say, no, the set of vectors, or the statement is incorrect, but the set of vectors does not span R4. And then I'm fine with any one of the following 3 statements or some variation thereof. There are only 2 pivots in our 4 columns. Nope. Lies. 4 rows. Right, we don't want to talk about columns here because columns is about dependence. I'm going to use that in my next argument, but that's fine. So we want to talk about our 4 rows. We could say there are only 2 pivots when we need 4 to span R4. that's perfectly legitimate as well. Then we don't have to worry about rows versus columns and which one's helping us with spanning. The last one is probably the hardest here. I was thinking about those non-pivots. We'd have to write something like, since 2 of the 4 vectors are linearly dependent. But see, now we're getting into definitions that we haven't hit at that point. It's probably not the best way to do this. We only have 2 linearly independent vectors, which is not enough to span. See, too many words. I think most students just went with this one, 2 pivots and 4 rows. But this was also nice because I'm going to have to think about the rows versus columns. We're able to just say, I need 4 pivots in order to span R4. There we go.